Welcome to this introduction to centrifugal pumps on this YouTube channel. Do like and subscribe this channel for more such useful videos. Over the course of this presentation, we will explore the fundamental principles behind centrifugal pump design, their key components, how they generate flow and pressure, and the critical operational considerations that every engineer and operator should understand. This module covers parts 1 through 3 of the centrifugal pump series. Centrifugal pumps are among the most widely used types of pumps in industrial applications, valued for their simplicity in both design and operation. At their core, these pumps consist of two main components. The first is the impeller, a rotating element driven at high velocity, typically by an electric motor. The second is the casing, which encloses both the impeller and the liquid being pumped. Let us examine Figure 1 to visualize this arrangement. Here we can see Figure 1, which illustrates the basic construction of a centrifugal pump. Notice how the impeller sits inside the spiral-shaped casing, also known as the volute. The liquid enters at the center, or eye, of the impeller and is discharged outward through the volute casing. This simple yet effective design is the foundation of all centrifugal pump operation. Let us now examine the purpose of each component in greater detail. The impeller's primary function is to increase the velocity of the liquid entering the pump. It achieves this through protrusions called vanes, which are an integral part of the impeller's structure. The casing, on the other hand, serves to convert this liquid velocity into pressure. Its spiral, or volute, shape features an increasing cross-sectional area toward the discharge, which slows the liquid down and thereby increases its pressure. This is necessary to overcome restrictions in the downstream piping. When the pump is in service, liquid enters at the impeller eye, which is the suction point. As the impeller rotates, in this case clockwise as indicated by the arrow, the vanes accelerate the liquid radially outward through centrifugal force. This is, of course, how the pump gets its name. Once the high-velocity liquid enters the casing, the gradually expanding cross-section reduces the liquid's velocity and converts it into pressure. The underlying physics here relates to the law of conservation of energy. Energy cannot be created or destroyed, but it can change form. In a centrifugal pump, kinetic energy associated with the liquid's velocity is converted into pressure energy, which is similar to potential energy. It is important to note that this conversion is not perfectly efficient. Some kinetic energy is inevitably lost to friction as the liquid flows through the pump. Another common centrifugal pump design incorporates a stationary diffuser ring, as shown in Figure 2. This ring consists of several protruding vanes similar to those on the impeller, but crucially, it does not rotate. The spaces between the diffuser vanes widen from the impeller rim toward the casing. When the pump operates, the diffuser vanes convert some of the liquid velocity to pressure before it even reaches the volute casing, where additional velocity is converted. This two-stage conversion results in a more efficient pressure buildup. Figure 2 provides a detailed view of the stationary diffuser ring arrangement. Observe the fixed vanes surrounding the impeller. The widening passages between these vanes act as small diffusers, gradually reducing the liquid velocity and increasing pressure in a controlled manner before the liquid enters the volute casing for further pressure conversion. Moving on to multistage pumps. The types of centrifugal pumps we have discussed so far are generally capable of producing maximum pressures of about 1,000 kilopascals. When higher pressures are required, simply increasing impeller speed or size has practical limitations due to material constraints and other engineering factors. These modifications alone are unlikely to meet requirements when pressures significantly above 1,000 kilopascals are needed. When higher pressures are essential and simple modifications will not suffice, a multistage centrifugal pump is the solution. In this design, multiple impellers are arranged in series. Liquid exiting the first impeller passes through a volute-shaped passage to the inlet of the second impeller, and so on through each successive stage. Pressure builds incrementally from pump inlet to discharge. Horizontal centrifugal pumps may have up to approximately 8 stages, while vertical configurations can accommodate even more. Beyond that, a second pump may be required. Figure 3 illustrates the internal configuration of a multistage centrifugal pump. You can see the series arrangement of impellers, each contributing an incremental increase in pressure. This stacking approach allows centrifugal pumps to achieve pressures well beyond what a single-stage design can deliver, while retaining the benefits of centrifugal pump technology, such as high flow capacity. Let us now discuss pump drivers. Since the impeller must rotate at high velocity to generate adequate discharge pressure, centrifugal pumps require high-speed driving devices. Electric motors are the most common drivers, with the motor shaft directly coupled to the impeller shaft. Typical operating speeds range from 1,200 to 3,500 revolutions per minute. Internal combustion engines may also be used for large centrifugal pumps, particularly in applications like firefighting where electrical power may be unreliable. Continuing with pump drivers, gas turbines are employed in certain applications, such as water injection systems, where pump speeds can reach 5,000 to 6,000 revolutions per minute. Steam turbines are used to drive larger pumps, especially in power plants where steam is abundantly available. In such facilities, steam turbines can be more economical to operate than electric motors and offer greater flexibility in operating speed. They may also drive smaller pumps where a plentiful steam supply makes them the practical choice. We now turn to the concept of pump head, a term frequently used when discussing pump performance. To understand this concept, we need to review a simple mathematical relationship. When liquid fills a tank to any depth, a certain amount of pressure exists at the bottom of that tank, caused solely by the weight of the liquid above it. This pressure can be calculated using a straightforward formula. The formula relating pressure and head is P equals 0.434 times H times the specific gravity of the fluid, where P is pressure in pounds per square inch and H is head in feet. This can be rearranged to solve for head. H equals 2.31 times P divided by the specific gravity. The key conversion factors to remember are that 1 psi equals 2.31 feet of water head, and conversely, 1 foot of water head equals 0.434 psi. These values assume water at 39 degrees Fahrenheit, where the specific gravity is exactly 1.000. To illustrate, consider a tank containing water at 39 degrees Fahrenheit, which has a specific gravity of 1.000. If the water depth is 3.28 feet, the formula shows that a pressure of 1.42 psi exists at the bottom of the tank. The formula can also be rearranged to find the depth. Given a pressure of 1.42 psi and a specific gravity of 1.000, we can confirm that the liquid height is 3.28 feet. In pump terminology, this liquid height is commonly referred to as the head of the liquid. Extending this concept, we can demonstrate that a depth of 2.31 feet of water with a specific gravity of 1.000 produces a pressure of 1 psi at the bottom of the tank. The equivalent head of 1 psi for water is therefore 2.31 feet. Applied to pumps, this means we can express pump performance in two equivalent ways. For example, a pump discharge pressure of 21 psi corresponds to a pump head of 48.5 feet. This head value represents the pump's ability to move liquid against resistance. Several factors affect a pump's ability to deliver liquids. These include the liquid levels on both the suction and discharge sides of the pump, the pressure in vessels connected to the suction and discharge piping, friction losses caused by the piping system, and the velocity of the liquid being pumped. We will now examine each of these factors in greater detail. Static heads exist when the liquid reservoirs on both the suction and discharge sides of the pump contain liquid. Whether the pump is running or not, the liquid levels in these tanks create a certain equivalent head. The term static implies a non-moving condition. Figure 4 illustrates one common pump configuration showing these static head relationships. Static heads exist when the liquid reservoirs on both the suction and discharge sides of the pump contain liquid. Whether the pump is running or not, the liquid levels in these tanks create a certain equivalent head. The term static implies a non-moving condition. Figure 4 illustrates one common pump configuration showing these static head relationships. Static heads exist when the liquid reservoirs on both the suction and discharge sides of the pump contain liquid. Whether the pump is running or not, the liquid levels in these tanks create a certain equivalent head. The term static implies a non-moving condition. Figure 4 illustrates one common pump configuration, showing these static head relationships. Figure 4 shows a typical pump arrangement with supply and destination vessels. The pump draws liquid from the supply vessel on the left and delivers it to the destination vessel on the right. Notice how the liquid levels in both vessels create static head conditions that directly influence pump performance. We will refer to this diagram as we discuss the various head components. Referring to Figure 4, assume both vessels are open to atmospheric pressure. The supply vessel is to the left, and the destination vessel is to the right. Notice that the liquid source is above the pump suction. The vertical distance from the liquid surface in the supply vessel to the pump centerline is the static suction head, which assists pump operation by ensuring liquid is forced into the pump. The static discharge head is the vertical distance from the destination vessel liquid level to the pump centerline. The total static head is simply the difference between the static discharge head and the static suction head. This total static head is what the pump must overcome. A slight variation of the previous arrangement is shown in Figure 5. In this configuration, the static discharge head is measured as the vertical distance from the pump centerline to the point where liquid exits the discharge piping. This represents the actual location to which the pump must move the liquid, and it directly determines the discharge head requirement for the system. Figure 5 clearly illustrates this alternative arrangement where the discharge point is above the pump. The static discharge head is measured vertically from the pump centerline to the discharge exit point. Understanding this measurement is essential for correctly calculating the total head requirements of a pump installation. Figure 6 shows another important arrangement where the liquid source is below the pump. In this case, the pump must effectively lift the liquid from the supply vessel. The vertical distance from the liquid surface in the supply vessel to the pump centerline is defined as the static suction lift. In reality, the pump does not physically lift the liquid. Instead, the rotating impeller evacuates air from the pump, creating a partial vacuum. Atmospheric pressure then pushes down on the liquid surface in the supply vessel, forcing liquid up the suction piping and into the pump. As shown in Figure 6, atmospheric pressure forces liquid into the pump when static suction lift exists. This means there is a practical limit on how far a pump can lift liquid. At sea level, atmospheric pressure is approximately 101.3 kilopascals. This physical limitation is a critical consideration when determining pump placement relative to the liquid source. Let us calculate the maximum theoretical lift. Assuming a pump at sea level achieves a perfect vacuum while pumping water with a specific gravity of 1.000, atmospheric pressure of 14.9 psi would force the water upward. Since 1 psi equals 2.31 feet of water head, multiplying 14.9 psi by 2.31 gives us a maximum theoretical lift of approximately 34.4 feet. In practice, the actual maximum lift is considerably less than this because no pump achieves a perfect vacuum and energy losses occur in the suction piping. This underscores why pump location relative to the liquid source is so critical. In Figure 6, note that the total static head is the sum of the static suction lift and the static discharge head. In all the previous examples, we assumed that the vessels were open to atmospheric pressure. In practice, however, pumps often move liquid between pressurized vessels. Pressure head is defined as the equivalent head resulting from the internal pressure in a closed supply or destination vessel. This additional factor directly affects pump operation. Importantly, in cases where static suction lift exists, a positive suction head can still develop at the pump if the pressure head in the closed supply vessel exceeds the static suction lift. Refer to Figure 7 for this configuration. Figure 7 illustrates the concept of pressure heads in a system with closed, pressurized vessels. Notice how the internal vessel pressures contribute to the total head calculation. This is a more realistic representation of many industrial pump installations where both the supply and destination vessels operate under pressure. Friction head is another important component that affects pump performance. As liquid flows through the discharge piping, its pressure decreases due to frictional resistance. The pump must overcome this friction to maintain flow. Friction head is defined as the equivalent head produced by frictional resistance in the piping system. Several factors influence friction head, including pipe diameter, where smaller pipes create more resistance, pipe length, where longer runs increase resistance, and the number of fittings such as valves and elbows, each of which adds to the total frictional resistance. Velocity head is the final head component we will discuss. A liquid moving through piping possesses kinetic energy due to its velocity, and this translates to an equivalent head that the pump must supply. It is worth noting that suction piping is typically larger than discharge piping, ensuring the pump remains full of liquid. This means the liquid velocity, and therefore the velocity head, differs between the suction and discharge sides. While there are additional head-related terms in pump engineering, we have covered the essential concepts for this introductory level. We now address cavitation, a critically important phenomenon that must be avoided during pump operation. To understand cavitation, we first need some basic thermodynamic knowledge. The pressure exerted on a liquid directly affects its boiling point. Higher pressure raises the boiling point, while lower pressure decreases it. For example, water boils at 100 degrees Celsius at sea level where atmospheric pressure is about 101.3 kilopascals. In Calgary, where atmospheric pressure is roughly 88 kilopascals, the boiling point drops to approximately 96 degrees Celsius. An important fact about boiling is the dramatic volume change involved. When water boils at atmospheric pressure, the resulting steam occupies approximately 1,600 times more volume than the original liquid water. Conversely, when steam condenses, it shrinks by the same factor. Published tables exist for many substances that provide boiling points at various pressures, volumes of liquids and vapors, and other thermodynamic properties. While a detailed discussion of these tables is beyond our current scope, understanding this volume relationship is essential for grasping why cavitation is so destructive. Here is how cavitation occurs in a centrifugal pump. As liquid enters the impeller eye and accelerates, the increasing velocity causes a local pressure drop. If the liquid temperature is near its boiling point, this pressure reduction can cause some of the liquid to vaporize, forming vapor bubbles. These bubbles travel with the liquid toward the impeller rim and casing, where pressure begins to rise. As pressure increases, the boiling point rises above the liquid temperature, causing the vapor bubbles to collapse suddenly back into liquid. Each collapse produces a powerful shock wave that can cause serious impeller damage, vibration, and bearing wear. The module on centrifugal pump operation will explain how operators can prevent cavitation. This concludes our introduction to centrifugal pumps. We have covered the fundamental principles of centrifugal pump design, including the role of the impeller and casing, how flow and pressure are generated, the various types of pump heads, multi-stage configurations, pump drivers, and the critical phenomenon of cavitation. These concepts form the foundation for the more advanced topics covered in subsequent modules on centrifugal pump components and operation. Thank you for your attention. Do like and subscribe the channel for continuous efforts.